Hello guys and welcome to a new lecture on SQL coding. So in today's lecture, we are going to study SQL indexes. SQL indexes are specialized database structure that they are designed to improve the efficiency of data retrieval operations on a table. SQL indexes function similarly to an index in a book. For example, in a book, when you want to find a chapter or some topic, you do not go and check the page one by one, but you go to the list of contents, find the page number, and directly go to that page. In the same way, SQL indexes works. They enable the database to locate specific rows quickly without scanning the entire table. So, like the previous lectures, we are going to work with the university database with several examples like instructor, teach, department, student, advisor, takes, course, prerequisite, time slot, section, and classroom. So here we can see a list of our tables. Select all from information.tables. So here we can see a list of our tables, and these are the tables that we're gonna work with them. For example, in the university database, indexes are critical for optimizing queries such as finding a course by its course ID or retrieving all sections taught by a specific teacher. Indexes come in several types, each suited for specific use cases in the university database. We have clustered index, non-clustered index, unique index, and composite index. A clustered index determines the physical order of data rows in a table. Since the data can only be stored in one way physically, a table can have only one clustered index. For example, in the course table, the primary key on course ID creates a cluster index automatically, and it ensures that course records are stored in order of course ID, which optimizes lookups by course ID. Then we have non-cluster indexes. A non-cluster index is a separate cluster that contains pointers to the actual data rows. A table can have multiple non-cluster indexes, in this way making them versatile for various query patterns. For example, a non-cluster index on department name in the instructor table speeds up queries searching for instructor by department. Then we have unique indexes. A unique index ensures that no duplicate values are inserted into the index column or indexed columns. The unique index is automatically created for primary key and unique constraints. For example, in the time slot table, the unique constraint on day and start time creates a unique index preventing scheduling conflicts for the same day and time. Then we have composite indexes. A composite index is created on multiple columns and it is useful for queries involving multiple conditions. For example, in the takes table, a composite index on course ID, section ID, semester, and year can optimize queries that filter enrollments by course and section details. So the question is how indexes works. Indexes enhance query performance by reducing the number of rows that the database needs to scan, exactly like find an exact page in a book based on its number in the list of contents. Indexes typically use a B tree or B plus tree data structure, and this B tree organizes index keys in a balanced tree in order to enable efficient search. You are well aware that a B tree is a self-balancing tree data structure that maintains sorted data and allows efficient search insertions and deletion in a logarithmic time by organizing keys in a hierarchical structure with multiple child nodes per parent. The database navigates the B tree using a binary search approach which cuts the search space in half with each step, making lookup much faster than scanning the entire table. For example, a B-tree index on student ID in the takes table allows the database to quickly find all courses a student is enrolled in. Alright, so here is our university database. If we want to see the performance of an index, we must have a large table. The data entered in our table are very small, so we have totally 13 records. We cannot see the performance of the indexes. So we need to create one big table. I'm gonna generate one new table, like student one, and I'm gonna add 50,000 sample records. So I will create this table, create table student one, and in here I will have the same attribute. So student ID is name of varchar 10 and it's a primary key. Then name is varchar of 50 and depth name varchar of, for example, 50, and total credit is integer. And let's see our table here, student 1, and this is our table. I'm gonna generate 50,000 sample data. For this one, I need to use a transaction. Later in a separate lecture, I will explain about transaction. So begin transaction and begin try here. So we use a number table approach for better performance. So with numbers as, and then in here, select top 50,000 row number, other, then here order by, and select null as n, right? Then from sys.objects a, then cross join sys.objects as b, and again cross join sys.objects as c, right? Then here I add to my table, insert into student 1. This piece of code that I write here is a kind of common table expression, and we name it as numbers. And this generates a sequence of numbers from 1 to 50,000. This is dot object. This is a system view that returns row representing object like table views in a database. Then we have here cross join. This produces a Cartesian product by multiplying the number of rows. So we use it to generate a large enough rows set up to 50,000. Then here this row number our order by select null as n. This assign a unique sequential number of n starting from 1 and to reach the row. And this select null here is used as a dummy order when ordering is not important. And then we select top 50,000. It means we limit the result to the first 50,000. So now we insert into student, and the attributes are student ID, name, depth name, and total credits. And here we go for select, then in here s plus right of 1, 2, 3, 4, 5 plus cast n as varchar 5 and 6. Then we add student because we want to make some exemplary data, right? Student underscore plus cast, and here n as varchar 10. Then here for the departments, we can define the different department names, right? Because we want to have different departments, right? So we go for a conditional statement. Then, for example, and the number that we have generated, mod 10 is equal to 0, then you assign these things as computer science, right? Then in the same way, we can go for the rest, for example, for biology department, electrical engineering, mechanical engineering, physics, chemistry, mathematics, history, economics, and we make one else here. So then we will change this one, for example, if it is mod 10 is equal to, divided by 10 is equal to 0. If, for example, for 11, 21, for 22, 32, 3, then 4, then 5, then 6, then 7, then 8, and the other case, it will make it as English. Okay, so I will change these departments now here as biology, this one as electrical engineering, this one as mechanical engineering, this one as physics, this one as chemistry, this one as mathematics, this one as history, and this one as economics, right? And then we need to close this one here. Then n mode 1 to 1 plus 30 because we want to add credits between 30 and 150. Then we will get all from the number that we have generated above. I'm going to explain this code again. This code is there multiple row into a student one table by selecting and transforming data from a source table like numbers that we have generated here. So this is like insert into, we insert data based on the column student ID name, department name, and total credit. Then this part here that you can see, this one, this generate student ID. For example, like S0001, S0002, and something, right? So these are some student exemplary data. And then here we create a synthetic student name, like student underscore one underscore two, and something like that. Then here we generated some values, right? So we assigned n mod 10, and this is a cycling through 10 department name that we have generated here. And this one is for exemplary total credits. Okay. Now, commit transaction, and we can try print here, for example, successfully inserted 50,000 records into student one table, and try. And next we go for begin catch, and here rollback transaction, and we go for print error inserting records plus the error underscore message, and we print the error message, then end catch, go. Okay. Commit transaction, this finalize the transaction that we have made there. It means making all changes permanent. And this is a message to print this one. And this end try and begin catch that we have, this is a standard SQL error handling block. And this rollback transaction reverse any changes if an error occurs, and then we print a message. So let's run this one. Objects. Okay, so now if I run this code, then I can see there are 50,000, right? So let's see the count. So select count star from student one. So you can see here, I have generated 50,000 data. So now I'm going to show you the difference in terms of time, access time, without and with index. So to do that, I need to declare some time. So declare and start time as date time, and end time and time as date time, and also duration. So these are the variables that I define, duration as integer, right? So let's run this one. Okay. Let's print here running query without index. Just print this one. And then set we assign the current date to the start time. Start time is equal to get date, right? Then I'm going to execute a query without the table. So select all from student one, where, for example, where department is equal to physics, where depth name is equal to physics, right? Then I'm gonna get the end time set at end time is equal to the get date. Then set the duration. Duration is equal to date difference between what? In case of millisecond between the start time and end time, right? End time. Then we gotta print query without index completed in. Then here we will cast the duration as varchar 10, and we can say like in millisecond. Okay. Let's run it. Some problem. and here. Okay, here we go. And you can see here query. So in message here, we can see query without index completed in 66 milliseconds. Now we're gonna create one index and compare the time with this one. So for this one, first we need to clear cache for accurate testing. This one we use a keyword dbcc and free pro cache, and also here dbcc and drop clean buffers, right? Now we're gonna create one index, right? So we're gonna create index and we call it as ix dot student underscore depth underscore name on student one, and the column is depth underscore name, right? Then so this is our index. It's already available. So I'll call it as one. Okay, have been made. Now I'm gonna run this one with index. So declare again, we will declare the start time and end time and duration. Start time as date time and uh, end date time, and end time also is a variable in the type of date time, and duration is integer, right? Then we print here that running with index, and then we get the current date and time of the system as the start time, right? Is equal to get date. So then we're gonna run this, right? So the same query here. Then we're gonna print the same here. So the end time duration in millisecond query with index. All right, so let's run this one. So what was the previous one? Was 66? 66. Okay, so let's see this one. 383 milliseconds. Okay, and this one I will remove the physics. I will remove the physics, and here you, no, that one is already available. This one only. And you can see 323 milliseconds, right? We understand that indexes help to have faster data access, right? This is just example. From now on, just I do not show you the time, just I show you how to create and drop the indexes, right? The first type of indexes that we're gonna try is a single column non-cluster index. A single column index speeds up queries that filter on one column. Here, we create a non-cluster index on department name in the course table in order to improve search for courses by department. So let me write this way: if exists, then I will check whether this index that I'm going to make is already available or not. So select name from system.indexes, system.indexes, where this is the name of the index that I'm going to make: IDX, course, depth, name, and here and object ID is equal to the table that I'm going to make this index course, right? Then here, if it's already available, drop this index, this one, and if it's not available, then create index, this one on course based on depth name column, right? Object ID is equal. No, not here. Object ID is equal to, again, object ID, correct. If exists, select name from sys. No, 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 no. Sorry, just I made a mistake in selection. Sys.indexes where name is equal to index department name and object ID in here on the course. All right, so we have generated one index. This is the index that we have generated. Now, this index is used for these queries. I select from course where depth name is equal to, for example, computer science. This index that we have generated here will help us for such kind of indexes, right? It helps us to have a very fast queries in this way. The next one is unique index. A unique index ensures no duplicate values in index column or columns, right? Although the primary key on instructor ID in the instructor table already creates a unique index automatically, we demonstrate the syntax by creating unique index on name in the department table, and we assume department name are unique in practice, right? So we do the same thing here. Just I change the name, and in here IDX, and then department name on the course of department, then this one and this one on the department and depth name. Okay, so this index has been generated. This index ensures no duplicate department names and speed up lookups by department name. Here, we note that the primary key already enforces uniqueness, so this is just for illustration. The next one is composite index. A composite index on multiple columns optimize queries with multiple conditions. Here, we create a composite index on course ID and semester in the section table, and our goal is to optimize queries filtering by course and semester. Okay, so we do the same thing here. And this time we call it as ITX section, course, and semester. Then the table that we're gonna make is section. So this one should be here, and this one should be here, and course ID and semester. Right? So in this way, we can generate these composite index. These composite index will help us for queries like this one. Select all from sec where course ID is equal to, for example, CS101 and semester is equal to, for example, fall, right? So this index will speed up the query in here, right? For dropping an index, just you go for drop index and just you use the index name, this one, on section, right? In this way, you can drop an index. Dropping an index can improve the performance of insert, update, and delete operations. But when we delete an index, it will slow down queries that relies on that index. So what are the advantages of indexes? Indexes offer several benefits in databases. They significantly speed up the select queries by reducing the number of rows scanned, such as finding a specific course by course ID. Indexes also enhance the performance on join operation, like joining the text and section tables on course ID, section ID, semester, and year. Unique indexes enforce data integrity by preventing duplicates, and indexes also reduce this input-output by providing direct access to relevant data. However, there are some disadvantages associated with indexes. Indexes come with the trade-offs that must be carefully managed. They slow down insert, update, and delete operations because the index must be updated whenever the table data changes. For example, adding a new section requires updating all indexes on the section table. Indexes also require additional disk space as they store copies of the index, columns, and pointers. Over-indexing can lead to excessive maintenance overhead, and fragmented indexes may require periodic rebuilding in order to maintain performance. My recommendation to you, in order to maximize the benefit of indexes in the different databases, adhere to several best practices. One, we should create indexes on column frequently used in where, join, group by, and order by clauses, such as course ID, student ID, or department name. We should avoid indexing columns that are rarely queried, as these waste space and also slow down write operations. We should use unique indexes for columns that must remain unique. For example, time slot, day, and start time. We should avoid indexing on small tables, such as department table with few rows, and table scans may be faster. And the last one is we should monitor index performance using database tools and rebuild fragmented indexes periodically. Okay, that's all for today. SQL indexes are powerful tool for optimizing query performance in various databases. By understanding the types of indexes like cluster, non-cluster, unique, composite, and also how they work, for example, B-tree data structure and binary search, and best practices, they can help you in order to improve the performance of your database. You can significantly enhance data retrieval speed while managing the trade-offs of slower writes and increased storage. It is better to start by indexing frequently queried columns like course ID, student ID, and semester, and use database tools in order to monitor and maintain index performance. With careful design, indexes will make your databases faster and more efficient. Thank you very much for your attendance. Please feel free to ask me your questions by leaving a comment below this video lecture. Thank you and see you in the next lecture.